Okay, thank you for that kind introduction, and thank you also for the invitation to speak. This is my third visit to Holland, and it's always a pleasure to come here. My special area is looking at wind loads on trees and the dynamic forces that occur, and I've been doing this study for about 15 years, and a lot of what I'm going to present contradicts what I see in the scientific literature. So I thought initially a lot of work that I was doing was incorrect, but after doing a lot of further work and publishing, I now will show you what I see on trees, and you can make up your own mind. My view of trees is as an engineer, which is my training. I don't really know that much about trees like an arborist does, but I'm going to do a structural analysis of trees. So a lot of what I do is not new. It's done in structures and buildings and machines. It's just being newly applied to trees in arboriculture. And particularly I'm looking at trees that are loaded by winds. As an outcome of this, just hold up the device. Yeah. As an outcome of this, I'm going to take you through quite a lot of sophisticated theory, but we wanted something that arborists could use and would be simple, that we can just put on a tree, turn it on, wait for a wind and tell us is the tree stable or not stable. So the outcome is actually very simple. We're going to show you some results from some storms. I want to also show you the wind environment. I find that at conferences and in conversations people talk about the tree a lot, but they forget about the wind environment. So a big part of what I'm trying to explain today is what, like a balance. It's not just the strength of the tree, but it's also the loads, and it's the loads and the strengths that need to be in balance. We need to look at both, not one. And we'll look at some case studies, and these results need some interpretation. Now, one of the things that I found over many years, and even last night I had a very nice pleasant dinner with some people whose background comes from forestry. So why are we here talking about trees when we know there are other people dealing with forests and that? What's the difference between a forest tree and a tree in an urban environment? And when we look at the trees, I found there's a huge difference in trees based on their size and their shape. And the latest research is showing this. Now, I'm going to spend an hour talking, but the thing I want you to remember is the big difference of branches. So what we see with the difference in the shape is that we go from small trees to slender forest trees to open-grown trees and to giant trees. Now, if we do a static analysis, which I haven't got time to talk about today, which is quite good and it's quite valid, we can actually do a static test on each of these trees, and we can scale results up and down. But with dynamics, we can't do that. The theory says we can't do that. So size and shape is very important, more so than species. So what we'll be concentrating on is large, open-grown trees. So my talk specifically is about this type of tree. And the difference is it's not small, it has proportions more. This one is mostly trunk, very little branch mass. This one is mainly branches. It's got a very small proportion of trunk. And the large tree, the giant sequoias, is mainly trunk. So the dynamics of each of the masses is what affects the dynamics performance in wind. So the emphasis in this biomechanics course and the workshop I'm running tomorrow is on open-grown trees rather than the small trees or the slender trees or the giant trees. The distinction is not based on species, but it's on their form and shape. And a lot of implications, this is after my lecture, I haven't got time to talk about this, is what's the effect of removing branches or pruning? How does pruning affect what happens in trees? Now, why are we talking about this? The real reason is that we've got a lot of branch mass in the tree. So it's not small, it's not trunk, it's not large. And I use the term open-grown tree rather than urban trees because the biomechanical principles are not unique to trees in the city, it's all trees of the open grown form. Now, the reason we're studying trees in wind is because failure in urban areas is a big issue and liability is a big issue. We don't want to make a mistake and get sued. And in conferences and in presentations, we use lots of images of trees falling over. Wind is by far the largest load on trees, and the large dynamic forces occur in these open trees because of the forces on the branches. The dynamic forces that only appear once we look at these trees are the forces of mass, which are called inertial forces. So when masses move, they have a force associated with that movement, and also the force of damping, where the energy is used up. Neither the inertial forces of mass nor damping occur in a static environment. You have to have movement for those forces to become apparent. So this is a photograph of a park in Melbourne, and I'm not sure if you can see up the back, but this is the sort of tree that I deal with. And there was a beautiful tree that was completely unpruned, just to show you the form of an open grown tree. If allowed, the branches actually come down and touch the grass, and if you think about it, there's no possibility of these branches breaking downwards. It's not possible because they're already touching the ground. But we prune them off, and I often ask the question when we see a branch test, and we see it in the literature, I'm going to show you one, catch a rope and you pull the branch downwards. But what I'm finding is when I measure that in wind, the wind load is upwards. That's why I say it's contradictory. So the characteristics of the trees that I'm talking about are roughly 10 to 60 metres high. So I won't be really dealing with smaller trees in urban environments. They're not the particular thing I'm looking at. It's where branches are a major proportion of the tree, and in winds, the sway is dominated by the branch sway. And I think it's the data set I'm using, and there's many references on trees in wind in the literature, but they're done in forests, and they're different types of trees. And one of the things about this, and this is some work from Ed Gilman, who presented here in 2010, I think, and this is a reference from his pruning studies. He built a wind machine and blew trees sideways, and the wind speeds got up to 110 miles per hour. This is a very high wind speed. He put sensors, not exactly the same, but the same internal part, same sensors on these trees, and came up with the conclusion it may not be wise to extrapolate these results to larger trees, because what these trees did, the small trees, doesn't necessarily occur in larger trees. If I've done something different, the only thing I've done different is I've moved the sensor from here down to the base, and I'll explain that. So what I'm doing in my mind is not very new, it's just a different application and understanding of what's happening. Now I'll briefly look at slender trees and show you dynamics. There's a lot of mathematics behind this, but I've tried to remove the mathematics, and to help me, and hopefully you, I want to see what the mathematics say. And that movement is what the mathematics say. So trees in wind, if you go through the scientific literature, the dynamics act like a pole. So it sways backwards and forwards. And this work, there's many works done in forestry. They use simple models of the pole, and the conclusion is that trees have harmonic sway. These scientific papers are reviewed, they're checked, they're correct in every way, but there's assumptions that aren't stated. And the assumption is the mathematical analysis treats the trees like a pole. And they might be Scots pine at 6,000 stems per hectare. So can we use the results from these studies for our work with urban trees? And if not, why not? And it's a very simple answer, but it's taken me many years to work out. It's because of the branches. These trees don't have the branch dynamics that the trees we deal with. Also in forest trees, they don't look at individual trees. All their modelling, all their work looks at the percentage failure in a forest, and they don't look at individual trees. They're also very slender. Some of the trees in the literature, I talked to a researcher in America, Mark Rudnicki, who did this, and he was looking at slenderness ratios of 160. That's 160 times the diameter. And I said to him, if you took one of your trees and removed all the other trees around it, the tree would actually fall over by itself, couldn't stand up. He said, yeah, I know that. But that wasn't stated in the paper. So those trees were very, very special type of trees. And most of the movement is in the trunk mass. Very small proportion of branch mass. So my question is, are those trees the same as open grown trees? Can we use the results in our work? And I'm now saying no, you can't. The other type of tree is a giant tree. And I've taken some examples from the internet, so I haven't seen this tree. But in these sorts of trees, the mass of the trunk is the dominant feature. It is so big it cannot move because of its inertial force. So the wind comes along and pushes on part of the tree, and it just cannot respond. It just doesn't respond because these inertial forces. So in this type of tree, the static method is quite applicable. So we would only use statics on this tree. Okay, so can you press? So to take all that and to look at what we are looking at, this is the sort of example I'm looking at. And if you have a close look at the wind loads on the branches, the wind loads upwards, not downwards. We've got lots of branches moving. It's a very dynamic situation. And what I've measured and published is the wind force on the tree is about 6 to 10 times what we can pull on it with a static load. So they're very, very big forces. And the branches sway out of tune. When we look at failure, and that's an obvious question to ask about this work, failure is where the load exceeds the strength. So how strong is the tree? That's only half the question. And already I'm talking to people who are asking about this case, what if a tree had this? I said, well, what's the wind environment? You need the wind information with the load to know whether it fails. Now notice failure may not be where something breaks or snaps. It could be like the crane where it just tipped over. So it's a balance, it goes out of balance. So we're looking specifically at overturning failure of trees with this equipment. We're not looking at failure of branches above that. That's some other work we're doing. And I mentioned at conferences, people use images of trees falling over and failures because it's very dramatic. I think what we forget to do is look at stable trees. What do stable trees look like? So these are the trees that I'm dealing with, and most of the trees that I go and put my sensors out on trees in wind are very stable, and I don't get much data because they're so stable. And the trees do not move in proportion to the wind in their base. They only get up to a certain point, and that's it. And the rest of the trees start swaying. If we get more wind, it breaks off. And these trees over here are about 40 metre high on the top of a hill, and they get blasted by winds. They're about 80 years old, and I get no data that I can present to you, even in big windstorms. And it makes me realise that those trees are the ones that have survived. All the older trees, or the younger trees that would have had some problems, have blown away, and these are the very stable trees. Now when we come, we'll be dealing with this more in the workshop. We use different terms, and I was involved in the ISA Tree Biomechanics Best Practice and was asked about the terminology. So I'd like to run through some terminology which is used in the industry, but specifically when I start talking, I'll use specific engineering terms. Now load is a general term, so if we talk about wind loads on trees, we're talking about what are the loads on the trees, but we don't have any specifics at the moment on that. We could look at the self-loading or leaning trees, which I think are a special case, and that's where we've got static weight of the tree acting all the time. You must be very careful of that. And then we have ice and snow loading, which adds a lot of different loading to the tree, and that's again a static type of situation. And if I look at the thing I guide look to guide myself is, what are the units of the forces, or the engineering terms we're looking at? Load has no units. And then we have static loads and dynamic loads. So one of the things I'm going to go through very briefly now, and I don't expect you to remember it, but in the workshop we'll go through this in greater detail, is to look at specific engineering terms. This is what I deal with. When I'm looking at the wind loads, that's a general topic, but I'm specifically looking at the forces on a tree. When we have pulling forces like tension in a rope, or if you want to build a structure, think of a spider's web or a hammock. Only tension forces occur in several structures. We have compression loads, which are pushing loads, and in wood the pushing down causes swelling, and compression loads are the opposite of the tension loads. In bending, if anybody wants to experience this, which I get people doing in workshops, if you lean over, you can feel the stretching on one side and the compression on the other. So in bending, we get a combination of those, and in addition we get shear forces. And if you can see this, a shear force is a sliding force, and you can see this is a laminated beam test, and see the layers sliding over each other? That's a shearing force that occurs, and that's where the layers of material slide over each other. And the final force is a torsional force or a twisting force, and nobody is talking about that yet. So when we start talking about the wind loads on a tree, I will drill down and look at what are the forces. We're looking at tension, compression, I mentioned bending like the static force, but in trees we're getting these torsional forces, and failure is where we understand all those forces, and where they all add up is when failure will occur. So we're working on torsion after Christmas, and in about a year I'll have some information on torsion on trees. Now when we look at the forces, we also have to look at the force in the material and the area over which it's spread, and this is the stress. And in engineering terms, it's the force divided by the area over which the force is spread. So you've probably all heard of the axiom of uniform stress, which is something Mathic published in the early 90s, and it's been very helpful to understand what's happening with trees. But we're not just dealing with wind loads and forces, we're now looking at the distribution of those forces. So, seeing you're getting some educational units out of this, there's my question. What is the difference between force and stress? So, I'll show you this visually. This is some equipment being used in America. This is done at biomechanics lab at Morton Arboretum. And NASA, their funding was being cut, and they were told, you have to go and get other applications, so they tried this on trees. And what happens, they spray dots on the outer surface of the tree, and with two very accurate cameras, with stereoscopic cameras, they can see the dots and they video it, and with software they measure the change where the dots move, and then they can map the stresses over the surface. They did this with rockets that went to space on the surface, and now we're applying it on trees. So the dots on the surface move, which is in engineering terms strain, stretch. You can convert that to stress, which is what we're really talking about, and we can map the stress concentrations. Where does the stress concentrate? And that will be where failure occurs. So if we can play this as a video of a branch pull, now I'm saying the trees pull the branch upwards, but they pull it downwards. And you can see here, the different colours indicate the stress. The high red point occurs there, and that's where failure occurs. The video is a bit jumpy because I had to grab it off the internet. But you can see the stress distribution mapped on the dots. The forces now underneath, this will be compressive force, and it doesn't break in compression, it breaks in tension on the top. But we can see where the force concentrates, and that red, which occurs in one frame, is the point where the force is concentrated, so the stress is highest, and that's where failure occurs. So we can do a lot of failure analysis, and this is done conventionally in engineering. Now when we start talking about dynamics, this is a very brief introduction, if you can click in there. This is how poles vibrate. So if we did an analysis of a tree and used the mathematics, the mathematical equation, the assumption in the paper, not stated, is that that's the movement we're looking at. We must get this motion backwards and forwards. Now poles can vibrate in what was called the first mode, and now we get into some complex multi-mode vibration theory. Okay, we've now jumped to 4th year engineering, and poles can vibrate in the 2nd mode or 3rd mode. We can measure, even with this instrument, we can extract from the data the energy of vibration, the harmonics. If people play musical instruments, we can have middle C on a piano and middle C on a violin. We can tell the difference because of the harmonics coming through. So the dynamic theory is quite evident. Let's have a look at, and that's what the first mode of vibration is. Let's have a look at some higher modes of vibration and what happens when you put branches on the structure. So if there is one thing to remember from this lecture, is that dynamics, once you put branches, and there's only 2 branches on the structure. This image comes off the web from Montpellier in France, where they're doing some excellent work on that, and they're modelling trees and branches. They've only got to 2 so far, so we have to get more complex. But you can see the great complexity and contribution that branches have to the swaying. If you can just click on this one, please, young man. This is some research work done in Switzerland on the impact tests on trees to monitor landslide movement, so big impacts. And if you click on the second one, this is what happens to the tree. We get the higher harmonic motions, and you see the snaking, that's the higher harmonics occurring. Because those higher harmonics have different energies, the top flips out, the force, the stress in the top, in that tree, it had never experienced that in its life in winds. The energy goes up the tree, the pulse goes up, and the energy breaks the top off. Now I can tell you for sure, after monitoring trees in winds for many years, this does not happen in winds. It does in certain circumstances. So the complex mathematical analysis of dynamics is very applicable in this situation. And you can actually see it occurring there, but you don't have to worry about it. So we can say, this is not part of what we're dealing with. So it's fun to see. So what are we dealing with? I've shown this before. No, just the left one. This is looking at trees. This is how I see trees. So I take videos of the wind in a large eucalypt. And I've taken many hours and I got sick of watching it. So I decided to fast forward. Suddenly I saw something different. So if you click on the right-hand side, it's the same image but at 3 times the speed. And what I want to try and show you is this is what I see. The branches do not move together. They're moving separately as separate masses. So the wind doesn't blow the whole tree. It blows part of the tree and part of the one branch blows this way, another one does something else. So this is a visual representation of a lot of the data that I measure, just to show you that, and you can't actually see it in real time. It's only when you video it and replay it that you actually see something else happening. Now what happens if we take branches away? Why are we studying dynamics? This will not occur in statics. The energy goes from the branch. These are the inertial forces. Why does that occur? What's not there? Actually, if you just started it, oh no, it's okay, please. What's not there? There's no leaves. And once he removes the branches, he's dealing with a pole. He's gone back to that simple dynamic case. There's no using up of the energy. There's no damping. All the yeah, just click it again, please. The energy goes into the mass on the tree, which is a human being. So the dynamics theory explains this quite clearly. And you're not meant to get amused with my ideas, you're meant to learn a lesson. The message is the branches have been removed from the tree, and the tree dynamics are dramatically changed. So that's a visual image to show why branches are important, because when I show you the tree with the branches on it, it's so beautifully adapted to its environment, so gentle, you don't see, it uses up the energy. So in this case, the arborist is the mass, and he becomes the energy goes into him. So some of the issues are safety. I'm not dealing with this today, but how to use this dynamics information in tree climbing and tree removal, as you can see, can be very useful. And we need to understand the energy transfers. And we still don't know that with wind energy transfers. So we're looking for new ideas and methods. Now this is NASA again, just to show you the complexity of branch movement. They use that same technology, and they can visually monitor the direction of each of the hundreds of branches on the small tree, and they pull it, and you get this graph, and this is similar to the graphs I showed, engineers showed, but visually you can see that pulling the tree is creating a very complex dynamic system. So that's about the latest technology and research. I asked them if I could have the data of this. I know the people who did it, and we worked together, and they wouldn't send me the data, because I can go through each of those points and do my dynamic analysis. And it took me a year, because they're friends, I was saying, why aren't you sending the data? They didn't keep the data, they just kept the video. So they didn't have it, but we can extract a lot of information. But what's wrong with that? What's not there? That's a tree, and they've done a dynamic test. What's not there? Leaves. So leaves aren't there, and I've just given you an introduction to the small, medium, large trees. It's a small tree. So can you use the results of that with no leaves up to large trees? I can definitely say no, you can't, but that's a very good start, just to show you the complexity. So that is a test on that tree. And more I'm saying, in order to study a large tree with open ground film in its own wind environment, we actually need to go to that tree. And that's where these sensors come in. So how do we measure the wind loads on the trees? This, not everybody agrees on this, but what I'm saying is you can never measure the force on the tree, because the force is on all the individual leaves. You've just seen the complexity of adding all those forces up. So what you can do though, is all that energy and all that movement must come down through the trunk and create this overturning moment, so you can measure the wind loads on the tree down at the base. That is possible, but we can't measure the wind force and the height. So to bring all that complex theory together, what we did was to try and create something simple to see, is the tree stable or not? And my boss came to me about 4 years ago and he said, we want something simple that arborists can just put on a tree, turn it on, wait for a wind, get the results, is the tree stable or not? So we've tried to put all that young woman just said to talk a little bit slower. Would that be better? How's my English and your understanding? Okay, thanks for that. So what we're doing is measuring the tilt angle of the base of a tree in degrees. Simple unit, accurate information, because everything that happens up in the tree must come down through the ground, through the base, and we see this as a measure of when the tree is stable or not. If we take our stress analysis and click on a tree, this is a small tree, and you can see the soil movement. Notice the movement at the back is upwards, the movement on this side is downwards, and this is some of the NASA stress analysis for tree failure in the soil. And we now have to talk about what sort of soil, the strength of the soil, and also notice it's a static pull, and notice it's a small tree with the top cut off. Now why do they cut the top off? If they leave the top on, all the numbers dance around and they can't get nice graphs. But that's what I'm saying, is that's the message. What's happening above there, the dynamics, is so different that the static test is only part of the answer. You have to include all the dynamic analysis. So these are the trees. I'm going to move on to case studies and new instruments. These are the trees that I get involved with, and with the council we asked the question, these trees had their roots cut about 6 months ago illegally. Do we have to remove them? Will they be safe in the next wind? So we put the sensors on the tree. Can you see the sensors there? Hopefully not. That's where the sensors are, right down the bottom of the tree at the base. They're coloured black. We often put a little branch over them to stop vandalism. So they're very unobtrusive. This is the previous model, which was white, and they're good for show, but we don't like them in the field. And we put one at the base, which is monitoring the tilt, and we put another one up high, which we call a control, because if we don't get any data from the base, we have to ask the question, is the tree stable, or the wind just simply didn't blow? So this tells us that the wind has blown very hard, and this tells us the data that we wish to use. And we're dealing with stable trees that are well anchored in the ground. We're not dealing with tilting trees or trees that are half high. We're dealing with stable trees, not leaning either. So there we have the control, and sorry, the base. We have a cage. There's other ways of protecting us. These are made in Germany and can be purchased from Argus. I'm told by my boss not to act as a salesman, so if you want further details, you can go to Jan Willem and he'll tell you the details of purchase cost and all that. And they're made currently by Argus in Germany, and we don't make them or sell them. We just use them. I design them and we sell them. How you get the data out, you remove the tree, the sensor from the tree, unscrew the waterproof casing, remove the micro SD card, and insert that in the computer. The data is uploaded, NSpec, makes their money out of writing a report. It's got GPS on there so that it draws a map off Google, takes a Google image, the time, date, all that information is there, and you can enter the tree information. So we can get the data, and they last for about 20 days. So here's the results of the tilt on a tree. The thing I always try and do, and NSpec insists on doing, is you must take a photograph of the tree so that you can see what sort of tree you're dealing with. So there's the tree, there's the sensor, it's got a level on it, and here's the data for 19th of July to the 8th of August, and you can see that's when the big storm went through, and there's the tilt data from the rest of the storm. At the moment, we're keeping all the data, we're not analysing all the data, we're just talking about the maximum tilt value, the peak. So there's a lot more in the data that we haven't begun to analyse, and in future there will be more sophisticated analysis. But just a moment, we're saying, what did that tree do in the wind? Over 20 days, the maximum tilt was 0.49 degrees. That's what the sensor said. What does that mean? And if we look at the wind data from the official government site, we can see the wind data went up to 60 kilometres an hour on the 19th of July and dropped down, so that's when the windstorm went through. If we look at a specific tree now over 55 seconds, from that information, the sensor monitors 20 times a second. We can actually see the wind coming through, the tree swaying, these are gusts of wind. Then a huge gust of wind comes through and the tree keeps swaying and gradually goes back to rest. So this is the extra information we get, and we can certainly now tell if one tree is moving more than its neighbour. What does 0.6 or 1 degree mean? This is a maximum tilt of 0.97 degrees, and I'll show you our interpretation of that at the moment. So notice that 0.97 can occur twice. In many, many trees it only occurs once in the entire storm. So how do we use that and say, is that all the information? Is that the same as a static test if we called the 0.97? If we look at the output, and this is in our report, the green is the sensor base for the tilt. That's the stability reading. The red for the control tells us that the wind is blowing. See, the red is much higher than the green. So that the tree was bending and swaying. The sensor up the top tells us that, but we use the evaluation of the tree stability at the base there. So there's my office, and they're the tree sensors that I use. Here's the record that we've measured on a tree that hasn't fallen over so far. There's 1.49 degrees. It was a spruce tree in the front yard of a friend of mine who had heard what I'm doing. He said, look, the tree's moving, come and measure it. So I did, and I got some really good data. And the 1.49 was used during a big windstorm. It was obviously moving the ground. You could see it moving, and it didn't fall over. But the data was used by the owner, not me. I didn't make any recommendation. I just said, this is the tilt reading. And he then decided to remove the tree. So he made his decision that the tree was moving far more than its neighbours in the same windstorm and was obviously moving. So there's the maximum value. Included in the information, we get the directional information. So if the wind comes in this direction, we can see that we get the directional information. And often, the maximum tilt is in more than one direction. And what this is showing, where we're doing research on this, is the tree plate is not symmetrical. It does different things in different directions. So we sometimes recommend for trees up above 0.6, we say we're not sure about it, it needs further monitoring, and try and wait for a wind from a different direction. Now here are the scales we're using. We've been very careful in our literature not to use the word risk. We try and only use the factual information of tilt. What is the tilt in degrees? But we have a range, a low range, a medium range and a high range, and you can see the colours we're using are obviously going to feed into risk analysis, but we're not saying that, so we're just factual with what we're saying. And what we're saying, which is a limit, is a tree will fall over after it tilts beyond some limit, and we call that the limit of stability. Below that it's stable, but afterwards, as I lean over, there's a point where it's too much. So we're asking the question, where is that limit of stability? And from the literature, I'll explain this more in the workshop, the research work, we're using 0.6 of 1 degree. We're saying below that it's in the stable limit, and above that, this is the yellow, we're not sure, it's certainly moving more than its neighbours. And then it gets beyond 1 degree, we say that's in the high range, we put red on it, and we say, look, we don't know, but it's higher than we would say is in the stable range. So they're the two limits of 0.6 and 1. Now I've published this on, we had 80 trees monitored around a city of Brisbane in Australia in a windstorm a few years ago. And of all the 80 trees, most only moved, there's the 0.6 limit. I can just do this. And this is the low range. We could only get 1, 2, 3, 4, 5, 6 trees that were moving above that. Most of the data was in the low range and looks like that. And last night we were talking about Jan Willem's company who have been using these sensors in Holland for 2 years. And there's the data sample for their results and what I published from Australia. So I was pleasantly surprised how similar the results are. So most trees are in the low range. Between 0.6 and 1 is the medium range, where we can only get a few, and I'm still waiting to get some data above 1 degree. It's very hard to get. And basically what that says, most trees are stable. So when we're looking at the business of managing trees, we want to manage the stable trees. Can we predict failure? When I started this, I thought maybe I'll be able to say that tree's going to fail or this tree's going to. We can't do that. We can't predict failure, but we can confirm that these trees are stable. So there's the Dutch data of 2 years, and there's the Australian data I've published, and most trees are in this low range. If we look at the tipping curve, and I've published this information, this is published by Wesley and used by Broody for the tipping curve. If you have a close look at this, they're saying that all trees tip over in a similar manner. These are the degrees. There's 1 degree. People like the scale's very hard to see. And there's 2 degrees. And all trees have failed by about 2 degrees. What we did is we used this as the start. We said, let's go and measure the tilt of trees in wind and see where we get. So there's that maximum of 1.9 for that tree I've shown you. The 5 trees are in this range. Most of the trees are down here. The static pull curve is stopped at 0.25 of a degree. When you do a static test, they stop the test there because they don't want to do any damage to the roots, and they interpret that as 40% of the tipping load. We're measuring up to above 0.6 in some trees and above up to 1.9, and we're saying 1 degree is the limit of stability. It's a bit of a guess at the moment, but it's supported by our data. Now these are some case studies of how we use the sensors. Typically this is a council, they manage the trees, they've got flooding during rains, the residents complain, so say, okay, we'll design a water catchment device. They subcontract out to a company who subcontracts to an excavation company. They get the position wrong, so instead of being up there, it's 10 metres down the hill, and they come and cut the roots of the tree. And the design people and the council, we didn't even agree this, that should have been up there, big fight over this. But they say, look, have they damaged the tree? And the roots have definitely been cut quite severely, down to a certain level. And what I do now is I come along with my sensor and say, look, let's wait for the wind and see how much the tree is moving. And we also monitor the next door neighbours. I don't want to just use a number out of a book as a reference. I use this tree as a reference. They're happy this tree is stable, it's a very similar tree, similar wind environment. Let's look at the tilt of several trees. So we monitor that. This is the wind data from a particular windstorm that we monitored. We've monitored this tree for 2 years, and the maximum wind gust is 50 kilometres an hour. Now in the workshop we'll discuss how you measure wind, because notice in Australia they also say the average wind speed over 10 minutes, and you can get very different information. Which wind speed should we use? Should we use the gust or the average? And in my opinion we need to use the gust wind speed, which is the maximum. So the maximum tilt of this tree was 0.14. We interpret that in the low range. We said the tree was within its limits of stability, it was not removed. We recommend annual monitoring because of the severe damage in the roots. It compares both to the tree next door, but also when you do this from 1 year to the next, we can say next year, what would the tilt last year? Was it more or less? And we've got the wind speed data, so we can get quite a good understanding. And the data assists the manager to make the decision. It doesn't make the decision for him. The manager looks at that, he's a trained arborist, he's worked with us and is confident with our analysis, and he's decided to leave that tree, and that's 2 years after it's been cut, it's not moving, it's quite stable. But it's no guarantee. We put a proviso saying under the conditions of which we've monitored to this stage, the tree looks to be stable. If a huge wind came along and took out other trees, maybe that one would go. We're not guaranteeing that we're not going to get that problem. Now here's some wind environments. This is a wind gust in Florida. And if you can click in there, jump on. Notice the wind is coming through, the leaderboard goes over here, weighs the dust, we get the flag, the pattern across the way. But notice this tree here, initially it's blowing one direction, it completely reverses. So if we can play that again, okay, notice, have I got a laser here? No. Notice there's a white card here, see this? If I like my finger. And this is what we're finding with our results. I get the data back and we know the wind has gone through a parkland. and we're now monitoring 20 trees around, and some trees over there, the data is completely different to the trees over there. I said, we've made a mistake. But this is what we find with the wind environment. That you might be out there, you get people saying, no, look, that definitely the wind came from this direction, the tree. But what we find is the wind environment is very variable. That's a flat area, and even in cities, the buildings create a huge difference. All that difference shows up in these readings. So here's another tree with the roots illegally cut. You can see they're taking out some gutter and repouring it. See the chainsaw cut through there? The residents were very emotional. They stuck this sign up saying, this is a beautiful tree, it's a 50-year-old tree. What you've done, terrible, shame, shame. So good. So it shows the community is very emotional with their trees. They don't want this tree removed. So the managers say, do we have to remove the tree or not? Let's wait for a wind. Now this is a typical wind in Melbourne. The wind comes from this direction, the big storm's coming from another direction, and we get the wind front hitting. So you can see the gust wind here went up to 80 kilometres an hour over a 5-minute period. So it's a very strong wind for a very short period. Now that's fantastic for my research because I know that the tilt data, the tree's been loaded intensely from a wind, and notice the directional information, we get that from a wind from another direction. So we know that tree got really heavily loaded. We also know, we look in the newspapers, the trees nearby blew down. So this is a big wind. Because an obvious question is, do we measure the wind at the tree? No, we don't. We rely on the official wind data. We know this front went right through the city. We know other trees went down. So the manager's happy that this tree was heavily loaded by the wind with this data. We're not using it saying 80 kilometres an hour this tree. We know the wind environment is very different. So it's a single wind front. So the answer was, in this wind, at 80 kilometres an hour, which was measured by the official government measuring site, the tilt was 0.14 degrees. So that's the information we give the manager, and he then assesses and makes his decisions. We don't make that. The tree is within its limits of stability. That's the phrase we use. We've had lawyers look at this phrase. We're not claiming anything other than the data, which goes on file. It's within its limits of stability under the conditions of monitoring. The tree is not removed, but obviously it's damaged, and obviously the manager wants ongoing information, so we recommend to keep monitoring that tree. Now in this case it's once a year. If it's a bigger tree with more damage, and people talk about fungal attack, you know, how bad is it? Well, we don't know, so we say monitor that all the time. Okay, this is those trees I showed you down at Frankston. Now these are old pictures. This is the electricity company and the water company and the gas company not talking to each other. And one company come and dug the roots to their pipelines, another company came and dug it again, and another company. 3 times it happened, all illegally. Who's to blame? Are the trees stable or not? So we used, that's a row of beautiful Norfolk Island pines. They're absolutely iconic. The people love them. The council wants to know, should we keep them or not? So there's all the data. And this particular tree in here, which is the one that I'm most worried about, is certainly moving within its limits, but more than the other trees. So we can point to an avenue of trees and say, that tree is certainly moving more. How bad is it? Not sure. So we're honest, we don't pretend we know more than that. So I'd say, look, we recommend keep monitoring. Is it going to get worse, or is it going to repair itself over time? So the data goes on file. This is a very important point. We have information, data. If we have to go to court and say, oh, you should have taken that tree out. Well, this is the data we used. The data is then put on file, and we can then, maybe we don't sue the company now, but if the tree does fall over, we'll have all this evidence to go to court to say this is the results immediately after excavation, and it prepares ourselves for the future with data that will be admissible in court. The future, we don't know. Will the tree survive or not? Should we sue? We don't know the answer to that. The tree may in fact re-establish its roots. This is a very sandy soil and we think this will happen. So a tree company will be hired to re-establish the roots and monitor. But we will regularly monitor the root plate tilt and we'll compare the future results with the results from this year. So the same information. And if the tree does fail in the future, we'll have all this historic information and visual evidence to say, yes, that excavation had a major factor. Now another case, this is in Burnie, Australia. I drew a map, seeing we're in Holland. I've come a long way, so this is where I come from, Australia. Maybe I should have it upside down. But in Tasmania, there's a city where they have 5 trees along the foreshore, and they want to keep the trees. This tree, particularly tree number 5, had its roots cut in a foreshore redevelopment. Again, illegally, all the specifications were there, but somebody came in and they did a lot of damage. So if we can click on this. Yeah. Thank you. I have 5 minutes, so I'm going to go to the fun bits. So the council had 2 arborist reports. They got an arborist report in and say, oh no, the tree's moving, we have to remove it. Oh, not sure. I've got another arborist report. No, the tree's moving, they've got to remove it. So we put our sensors on there, and if you look very closely, there's a crack down at the base, and I go out in the storm, I'm a bit of a storm chaser, and can you see the movement of the tree? Okay, so this tree's clearly moving, got to come out. So we monitored with our sensors, then I took them back to the lab and said, how much is it moving? I don't know how much it's moving. This is a replay. I've written a computer program where I can replay the data. So this is in real time, and this is showing what the tree's doing. This is if the wind isn't blowing, and here's one gust of wind coming around. And you can see the gust of wind lasts several seconds, and then the tree gently comes back to this point. And the maximum wind load, we don't know the wind load, through the night we got the maximum tilt, and notice the wind front came through here, but associated with this was massive rain came with the wind front. And that's something we haven't begun to talk about, is the rainfall in a wet environment. So when we compared all the trees, we see the graphs did the same thing, and in the middle, the tree up the other end at 0.40, it certainly is moving more than the other trees, but again it's within its limits of stability. So all the trees recorded in the low range, we could give the exact information of what we measured. The outcome is that the manager had a decision. If one tree came out, they were going to take all the trees out and replant them. And the community was very unhappy with that decision, so they decided to leave them all. And all trees, and they saved a lot of money by not removing them, kept everybody happy. We did cable 2 trees back for several years, re-established the root plates, and we monitor every year, and the tilt of that tree is getting same as the other ones, so our conclusion is the roots are re-establishing. And this has been written up in a journal, the UK Arboricultural Journal, if people want a reference of it. So this is a storm in Brisbane. Where do we see this going? This is a research we're doing in Brisbane, which is in a subtropical area with beautiful trees in the council. And people are very busy. They're managing 150,000 trees. The big storm goes through. We chose tree sites along the riverbank. After the storm, each site has several trees. The green dots say all the tilt values are in the low range. These trees, these sites, have tilt in the medium range, yellow showing the not sure range. One tree did fall over. And this is where you'd send your tree crews. So this is 100 trees. We can't go through the tilt date of every specific tree, but we see this is made up for PowerPoint, so it's not working yet, but this is where we see this in the future. We can actually manage the trees in the city, not every tree, not 150,000 trees, but the main trees you're worried about, the tall trees in high profile areas. We map every tree on every site, and this was a site where we didn't get any tilt data high. So we say, okay, we know that site, there's the data, each tree and the data, we've got a lot of information, but don't worry about it. Green little lights there, you don't need to send any tree crews there. Here's another site, we've got most of the trees, but we have a red, the arrow shows a tree fell over, and the two orange show the trees were in the not sure range, so you'd send tree crews down there. So we see this as something that we can use in management in the future. And if we do have to go back, and we'll show this in the workshop, we can look in detail at the till history of each tree, and there's some stable trees. That's a leopard wood, some very nice trees around there. So in summary, we can get a complete information after a storm of the stability of the trees. So because I'm running out of time, and there's the wind environment, we can look through, we can actually manage for a particular site based on the history of its wind. I just want to go to the failure. A special point I must mention before I finish, we cannot predict failure on this. So people, and I thought we might be able to, but we can't. But how do trees fail? And this comes from a reference of Hale in 2010, and it's very good paper because it deals with the assumptions that people make in the scientific literature. And the assumption in all wind damage risk modelling, i.e. forestry, is that the extreme or the maximum wind loading in a particular storm is the key factor in determining whether damage occurs. Biggest wind load, that's when damage occurs. However, this has never been verified in field experiments, and during storms it's possible that root fatiguing, so gradual, hour upon hour, bit by bit, the fatiguing of the root occurs, and the damage occurs over a number of storms, not in one storm. And that's what I think happens and why these sensors are useful, because we actually see this tree starts moving in this storm, it's weakened, and it will probably blow over in the next storm, or there's been two storms up. So I'll just finish on this, and this is a video of a tree actually falling over. What we see when the tree falls over is after many hours of a windstorm. Now you can laugh. So nothing will stop a good arborist. So I think that there's a lot in that, because it shows a tree failure. But we want to get the information. And finally, sure, how do we manage trees? Now this is going beyond my expertise, but it's how do we use this information? And many times, this is the image you'll see in newspapers, it's the image you see in conferences, and a lot of management's based on fear. I think that's true. And one of the nice things with these sensors is we can identify trees that are stable that we don't need to remove. And I'm also, in the workshop, we'll be talking about how engineers manage buildings. And sometimes the buildings disappear, but the trees don't. Those buildings are not managed to failure. They're only managed up to a certain wind speed. If we get an extreme wind going through where the building goes, no one gets sued. But all the time tree managers are asked, when will the tree fail? I say, I don't know. And maybe we should be looking at the same design wind speed that engineers use. So thank you for listening, and I hope you've enjoyed the presentation.